Hey everyone, I get to go out to Brennan. What luck do I have? Great. A little bit about me. So I've been an early contributor to Docker and to CoreOS. Actually, the creator of the Deus project and its benevolent dictator for life. And as of about a month ago, I'm now the CTO at Engine Yard, which I'm really excited about. So first, just quickly, what is Deus really? We're the leading Docker-based PaaS, and by PaaS I mean sort of a solution that provides an end-to-end developer workflow. So build, config, release management, integrated routing, logging, things like that. It's really an opinionated developer workflow for software teams. And one interesting point is that Deus actually is designed to consume orchestration APIs. So we have prototypes of Deus running on top of Kubernetes, on top of Mesos, as well as Docker Swarm. So I want to spend just quickly a little bit on how does Deus work, so you can kind of get a little feel for the parts, and then dive into the lessons learned. So just real quickly, a basic system diagram of Deus. Really, the platform split into a control plane, a data plane, and a router mesh. So operators will typically stand up the control plane and the data plane using Fleet and etcd, and a developer will interact with the control plane through the router mesh to do things like configure applications, push code, scaling events, that sort of thing. And then there's a nice little scheduler abstraction, or what's really turned into an abstraction to different orchestration systems that will then run containers across the data plane, which could be really your scale-out portion of the infrastructure. So for our control plane, we've, there are some stateful bits to this. So what we actually did was we rolled a Ceph cluster. It's actually a containerized Ceph. It's based on some of the work done by the Ceph community. And you can actually run this, and lots of folks do run this Ceph subsystem to power stateful applications outside of Deus, and I'll talk a little bit more about that. But have a registry, Docker registry that we use to model immutable artifacts in the platform, Postgres database, syslog server, builder controller, typical things you'd expect for a PaaS control plane. On the data plane, this is really where the work gets done. Some type of scheduling system, Kubernetes, Mesos, or in our case today, Fleet, will drop containers onto hosts. And we have a service that will do some publishing to a routing mesh. We also have a service that will do log routing to pipe logs back to the control plane so they can be accessed by developers. Another look at this is kind of from a workflow standpoint of what happens on a Git push, which is a popular interface into the platform. That'll hit our builder in the control plane, and we really follow the 12-factor model of build plus config equals release. And that release gets modeled as a image, an immutable artifact inside of a Docker registry. And that's how we we do this all on behalf of users, and we talk to a scheduler from that point, and that will drop the containers, perform rolling upgrades, that sort of thing, and through etcd, publish these containers to a router so we can serve up what is typically HTTP traffic. That's kind of how the platform works. So how do we choose CoreOS? It's actually really interesting. As Kelsey mentioned, we've been around the CoreOS block for quite some time. It was in winter of 2014, and I'll never forget, we, like a lot of people, were faced with this question of, well, we have Docker image. We need to go to a set of containers across a distributed system. How do we do that, right? Early on, we were prototyping lots of different stuff that was out there. Our philosophy is really to sort of focus on the workflow components, what the software team really wants to use to consume, and then leverage open source tooling to provide orchestration and things like that, and really be laser focused on our layer. So we did some early prototyping with Mesos using the Marathon framework, the Flynn project SAMPI scheduler, and Fleet with CoreOS. And we tried to get Mesos or Marathon and SAMPI working. We got Marathon pretty far along. SAMPI we couldn't get off the ground. And Fleet miraculously just worked. And this is back with Fleet 020. And I was just shocked because I was expecting a ton of modifications would have to be made. And so what I ended up doing is one of these big sort of, with Deus at the time, it was kind of a rewrite the world refactor to actually merge CoreOS Fleet. Brace yourselves and all the appropriate warnings inside the PR. And we ended up merging it, and we ended up announcing this, I believe it was May of 2014. our 0.80 release, which is where we integrated CoreOS. And this is, in retrospect, one of the best decisions we probably made for the project by basically just choosing to adopt, as Kelsey said, the CoreOS stacks more or less wholesale. And why do we do this? Well, in our evaluation, it became very clear that CoreOS was truly the best operating system out there for running containers. Designed for that from the ground up. It was designed for distributed systems. It ships with things like etcd and Fleet, which are critical building blocks that you're going to be rolling your own if you don't have equivalents already. And really importantly, it was clear that they had a strong team with a strong philosophy, specifically around securing the internet and some of the stuff that they were doing with regard to updates, and that was really attractive. So it worked, though. That was really the biggest thing, was that even at Fleet 0.20, the damn thing worked, and I was just shocked. And I remember giving a demo to them on Vagrant. I was at their office at the farm, and I was sort of shocked that everything just kind of worked. I was expecting everything to break down, as demos typically do. So, and this has worked for us as a project, right? So Deus is, you might have heard of it today. Our download stats are showing we're doing, it's really more than this, but from at least 500 new clusters a day are going up of Deus. At least 3,500 new nodes are going up every day, and we're a little bit over 120 external contributors on the project now. And I credit, the work that CoreOS has done to enable this, really greatly. So what's next for us? V2 orchestration previews. We're going to be shipping new previews of Marathon, Kubernetes, and Swarm for orchestration to complement sort of Fleet, doing a core update integration and some enhanced developer UX. But let's get to what I really want to talk about here, which is lessons learned that we've learned along the way using CoreOS. The first one. Docker and systemd is really awkward, right? And really the reason for this is that Docker reparents containers. And when you run a container inside of Docker, what really ends up happening is you run this sort of client, which interacts with the daemon, and those are sort of detached, and the container that you asked for is actually spun up in a completely separate process tree. This completely breaks systemd, or at least the way systemd is sort of intended to run containers. Systemd went through all this trouble of setting up an IC group for you, and has all these tunables for managing things like CPU shares and block device I/O and all that stuff. But you don't get any of that because the Docker daemon is basically the point at which you're supposed to control a lot of that. Docker sets up the final C group where this stuff lives. And now, if this was sort of just a run-of-the-mill integration problem, that'd be one thing. But we've actually seen that this can result in orphan containers, and we've actually seen this at scale. If the Docker client and the Docker daemon can lose sync, you can actually wind up with containers getting orphaned on the Docker daemon side. So, second lesson we've learned: operating etcd is hard. It's not simple. One of the first things you get when you walk into CoreOS is you think, well, it's just going to be, I'm just going to launch a bunch of instances and etcd is going to configure itself. Not quite that simple. So the first thing you want to know is you really got to watch your disk I/O. As part of being a CP database like etcd is, consistent and partition tolerant, the consistency component of that requires that all the writes to etcd actually get flushed all the way down to the underlying block device. And if you have poor or more likely inconsistent network I/O, disk I/O performance, if you're running on EBS, for example, you are going to experience pain, a lot of pain. And this is going to result in leader flapping and heartbeat failures, and you're going to have a bad time. So you can monitor heartbeat stats with the V2 stats leader endpoint, which will sort of track this. And one of the things you should be checking is, of course, your mins and your maxes, but also your standard deviation for what your heartbeats are. And if those are too high, that's going to be a problem for operating this. Another thing is use an isolated etcd cluster when possible. It's really easy to get going with a simple cluster and use kind of the integrated etcd, but when you start moving into production applications, you really want to separate out those workloads and make sure that nothing else is running on those boxes, because the implications of some process going haywire if things aren't tuned properly can be really bad, and this is not a component that you want going haywire. Third lesson learned, Fleet works best as a distributed init, which is funny because that's actually how it's billed on the website. So the way that I look at this and the way that we're using this is you can really use Fleet to manage your cluster's control plane. And if you're building platforms, you know what your control plane is going to consist of. Maybe Kubernetes, or may have elements of Kubernetes, or different things you want to do. Fleet is really the best way to manage this stuff. Now, it looks like these did fit on the slide mostly here. You can use constraints to get granular placement. Now, when you're operating like a 3 or 5 or 9 node control plane, using placement constraints becomes really important because there are certain components that you're not going to want to have running on the same box. There are certain components that you are going to want to have running on the same box, colocation, and there's certain areas where you're going to want to do metadata for different types of machines. Now, is this as sophisticated as something like labels in Kubernetes? No. But this is extremely useful for standing up something like Kubernetes on top of CoreOS. And that's what we use it for with Deus, and that's what I'd recommend you use it for yourselves. It's also incredibly useful due to this feature that was added in, I believe, Fleet 080 called global units. And global units, you can typically tell, they do this thing where they mount in the Docker socket if you're using them to manage Docker containers. So these are things like log monitoring systems, or update systems, or really anything that's going to perform some type of host level management function. Be careful with these, because when you roll a new global unit across the system, it's actually quite nice, because when hosts add themselves to the cluster, or these global units are automatically loaded onto the box, and that's a pretty powerful scheduling construct. But the problem is, when you need to update them, you actually have to kind of tear down all the global units and roll out new ones, so they can pose kind of a management problem that way. Another thing, lesson number 4, Fleet unit files tend towards chaos. And those of you who have used Fleet specifically, you'll know what I'm talking about here. But let me walk you through kind of how this happens. So the first is that you realize that pre and post container execution actually becomes important. And in the beginning, you think, well, I'm just going to run a container, remove it, on the fly, and that's going to be the end of it. But no, not quite. Really, what you need to do is you need to prepare the image that it's running. You need to prepare the container, and oftentimes you need to remove any pre-existing container that may have been there and that had been orphaned. Then you do the running of the container in the foreground. And then you have to do some cleanup. And ideally, you want to make sure that you're not failing on error. Otherwise, the unit goes into a fail state. So the way I've showed this here is as nice little binaries that are doing all of this work. But that's not actually what happens, because if you load the binaries on the box, you actually have to update those over time. And that's not actually easy. So what you really end up doing is using subshells, because subshells are the only way that you can actually get this sort of setup and teardown for the container logic embedded into the Fleet unit. So you can just submit the unit, have it do everything it needs to do, including all the prep and cleanup, and then tear it down. And as that cleanup and things evolve over time, you really want that as part of the management unit, that you're submitting to Fleet. And then, of course, over time, these subshells quickly become complicated, where you need to chain commands together, use shell environments, and that sort of thing. So if it was only our project that was doing this, I would think, well, maybe it was just us. But I see this everywhere. Lots of folks with quite complicated unit files. Lesson number 5, container failover is hard. It is incredibly hard. Thundering herd is something a lot of folks hear about it, and one of the easiest ways to visualize why this is a problem is, imagine you have 2 sort of availability zones, and your cluster is running at 80% capacity. So you think you got 40% in one AZ and 40% in another. If you lose an AZ, you basically got 40% of your cluster capacity shifting over to the other AZ. And not only will you overwhelm the resources in that first AZ, but you're also going to find that downloading the images as you're in the process of crashing your cluster is going to prove probably the first thing that's going to take it down. And so this is where you get into things like scalable registries. And one of the things that we're looking at now is actually running registries as an agent on each local system and querying the local system as your pathway to downloading images. And that sort of distributes the load across the cluster, so you don't wind up with sort of Docker registry download bottlenecks inside of your infrastructure. Lesson number 6. stateful containers are hard. I appreciate it when the folks on the Kubernetes team and others are saying just don't do stateful containers. The reality is, especially when you're building platforms, you have to do some state. And we actually run a Postgres, registries, logging systems, and these systems all have to survive the failure of a host. So one of the things that we learned in this process was that Ceph makes stateful containers possible. And it's actually a really fantastic solution if you haven't messed with it. It has 3 different input interfaces. The first is sort of a S3 or Swift style API for blob storage, which is incredibly powerful. It also provides a block store API, so you can actually mount a block device, and that's distributed across the cluster. And then the last is a POSIX file system API via CephFS, and that's provided via a metadata service. Now, Ceph is complicated, and it's complicated because it's got a lot of components, and it's complicated because storage and state is hard. But you basically are shipping monitors, which are best described as sort of Paxos for every write performed on the cluster, which is pretty intense. You have OSDs, which are storage daemons, which actually store sort of a placement group of different blocks across the cluster. You have gateways to facilitate access to the blob store interface, and metadata servers, MDSs, to facilitate access to things like CephFS. So a lot of moving parts with Ceph, and since the monitors are actually Paxos, you have to manage those much like you would an etcd cluster, and maintain quorum and things like that. The other thing is, as you would expect with something like this, it has a ton of operational overhead. So, here you can see us entering, a store daemon on a host and running a Ceph-S. And look at all the stuff you have to worry about here. You have, of course, the health of Ceph reporting OK. Well, that's good. You have a monitor map. So we have 3 monitors, which is kind of the Paxos quorum here. We have a metadata service map. We have a OSD map, and we have a placement group map. And this all results in a certain amount of storage available across the entire pool of nodes. Now, in one way, this is awesome because really what you can do is add store daemons, these sort of OSDs, to the scale-out portion of your cluster. And as you add nodes to the cluster, you're adding storage capacity. And you only have to sort of worry about managing the monitors and the Paxos bits. But this is really, really tricky to operate at scale. So we actually try to restrict this. What we tell people is don't use our Ceph for anything other than the Deus platform. Because if you do, you can impact platform performance, and you're going to have a bad time. So what folks will do instead is they'll actually take our Ceph containers, which are the Deus/store-star, and you can actually run your own Ceph cluster on CoreOS using our unit files, and it's all completely reusable. So if you're in the mood for some pain, go check this out. The 7th lesson we've learned is Cloud.init is amazing, but be careful with it. It is, folks tend to try and do a little too much with it, in my experience. So the first thing I'll warn is don't use Cloud.init for configuration management. Though it's really tempting, and this is really kind of a snippet, an edited snippet of what our cloud config looks like today. It's incredibly easy to do something like, we need to increase NF contract connections in order to assist with etcd performance at scale. And so we just added it to cloud config, and over time we just add more things to cloud config and more things. And what ends up happening, with some of these larger clusters is the hosts get out of sync, right? And it's easy to say, oh, well, we're just going to deprecate those hosts and roll new ones. But the reality is that failover makes that a little bit painful to do in the real world. And so try to avoid this if possible. Try to be really, the way I like to think of it is everything you put inside of the cloud config, especially things like new services and stuff like that, or configuration tunables, is a little bit of technical debt with regard to CoreOS. You should really be moving that stuff into containers and agents that can perform that stuff in a more scalable model. So when it comes to proper configuration management, you should really be looking at some tools that do this out of the box. Like Ansible, for example, is designed to do config management over SSH. CoreOS supports SSH, hence that's a good fit. And another option here is Core Update. And I don't know if you've had a chance to mess with Core Update, but it's incredibly cool, and it's something that we're looking at to solve this problem of how do we keep boxes, CoreOS boxes, up to date. So lesson number 8 is, the CoreOS update engine rocks. It is just the coolest thing ever. If you guys haven't messed around with it, it's based on the Omaha Protocol, the Go Omaha library. The CoreOS folks have been nice enough to open source, and we just love it. One of the cool things that you can do if you haven't messed around with this is if you're running on stable, the CoreOS stable channel, you can actually set up CI jobs fairly easily to test your infrastructure on different channels. So if something's coming down the pike in alpha, you can actually get notified that it's going to break your builds at some point. And this is really important because with the whole update philosophy of CoreOS, you don't want to get surprised when a new kernel module rolls out or a new Docker version rolls out, and that ends up breaking your environment. So this is actually a test that we run against the beta channel for CoreOS, and as you can see, this one hasn't broken. I'll tell you, there's a reason I didn't use the screenshot for alpha, because that one looks a little different. However, this is also a snippet from the Deus skeletons in its closet here. We actually have to disable the update engine. So after telling you about how cool it is, I'm telling you that we turn it off by default. And the reason why we turn it off is because the failover of the units on our system is too painful to just have happen at any time. We've learned that it's important that an operations team or whoever's operating the cluster has a say on when a host goes out of service. Now, that's you could argue correctly so that that's really a failure on our part to build components that don't have that kind of the speedy failover that would make this possible. But if you're running databases or things like that, and you're talking about even 20 or 30-second failover, which is what we're dealing with for our control plane, for the Deus control plane, that even is too much to bear without sort of a guaranteed maintenance window. So we're looking forward to the day where we can turn that off, but we're not quite there yet. So be careful with that. And another thing I would recommend is explore using Core Update and the tooling with it yourself, because it can actually be extremely useful, like we're exploring with Deus, to manage your control plane on the CoreOS platform. So funny, Core Update is coming soon to Deus as of 9 months ago when I first demoed it at a meetup. So I promised this a while back. We are still working on it, but I've been a little consumed with some other stuff. But we are actually going to be shipping this probably in the next few months here. Number 9, and this is really getting into kind of the higher level bits here, is get your ops stories straight. CoreOS is kind of a foreign concept to many operations teams. And I know a lot of folks in this room have bought this stuff hook, line, and sinker. But one of the first things that we ran into when we were bringing this to different teams around the country was, this is foreign to folks. And it's really important that you have crisp answers for things like how you do networking, how you do logging, monitoring, security, updates. If you don't have crisp answers for folks, they're going to say, this is too new, bah humbug, I want to stick with whatever it is that works. The truth is there are really great answers for all this stuff. They just look and feel a little bit different than what you might get in a traditional operating system. And if you're looking to roll out CoreOS in your organization, this is my biggest piece of advice: is get crisp answers for how this stuff is going to satisfy your operational requirements. And then the last bit here I want to just mention is, we've really learned that CoreOS is constantly evolving. From the day one of us working with it, all the way through to today. And there's a couple things I wanted to kind of point out. First is etcd. I mean, when etcd first came out, it wasn't really clear that it was going to take the world by storm in the way that it has. It's used by every major project that you can think of today is running on either etcd or something closely modeled after it. etcd itself has undergone quite a bit of change, including a rewriting of the underlying Raft protocol, the sort of V2 that's coming out now. But we really, I really just kind of sit back and have to, thank the team at CoreOS for all the work that they've done to, to make etcd the kind of bulletproof piece of infrastructure that it is today. Kubernetes. I know the CoreOS team isn't directly responsible for Kubernetes, but I think it's fair to say that they've probably done more than any other company out there to make Kubernetes accessible, especially the work done by folks like Kelsey, to kind of spread the word about Kubernetes, but also provide a platform on which Kubernetes can run really easily, and provide a way for folks to kind of poke around at it. And there's no project out there that has done more to kind of advance the way we think about container orchestration and container clustering at scale than these guys, and the CoreOS guys have a lot to do with that. And of course, Rocket. Rocket was obviously released to some controversy, but the very interesting thing to me about Rocket is I never meet anyone who says, well, Rocket is just technically inferior. That ever happen? I mean, it just never happens, right? Folks might argue about sort of the spec and what might be better or worse, or PR bits and a lot of the fighting that that folks like to focus on. But the truth is that Rocket is in some of the discussions that I've had with Alex, rooted in a real set of requirements that weren't actually being solved by the Docker engine. That as well as the desire to build from a spec forward are very valid reasons. And I'm personally a believer that competition is going to be really good in this ecosystem. We're in the early days. This is sort of the first inning for this new world of containers, and a technology like Rocket is a pretty important advancement in that effort. So I want to thank the CoreOS guys for their work on that. So that's it. I know I hopefully left some time here for questions, but thank you everyone.